Hello, Wharton Warriors. Today, I'm going to talk about maximum likelihood estimation, MLE, in statistics. So MLE is a parametric method for estimating the data density. Of course, just by hearing this definition, it is challenging to understand what MLE really is. So let's explore more MLE with example. So suppose we have obtained the following 5 data points. I'm going to draw 5 data points on the x-axis like this. We have 1, 4, 5, 6, and 9. So these are the data points. Assume that there are 2 probability distributions, one like this and one like this. Okay. Just by looking at the plot, which curve, red or blue, do you think it is more likely to have generated this kind of data? Even visually, it seems like more the data X was drawn from the red curve rather than the blue one. So this is because the distribution of the observed data appears to align more closely with the center of the red curve, like this. This example shows by observing the data, we can estimate the characteristics of the distribution from which the data was likely drawn. So here we assume that the distribution is normal distribution, and we try to estimate the mean of this distribution. Let's talk about the contribution of each data point to the likelihood. It just refers to the probability that the observed data came from this distribution. To calculate this probability numerically, we can compute the likelihood contribution. So we calculate the height like this. These are the heights, right? So we calculate the height for each data sample and multiply these values, the green ones, instead of adding them, because each data point is assumed to be independently drawn. So by calculating this probability for all potential candidates and comparing them, we can identify the probability distribution that best explains the observed data. So mathematically, we can express the likelihood for the entire sample set as follows. As you know, the joint probability density function for the entire sample set is called the likelihood function. So I'm going to say the likelihood function at P of X given theta. So theta could be mu, the mean, or variance. Parameter, the theta that maximizes the likelihood function is considered the most plausible value, estimate, theta hat, the original value. So theta hat maximizes the likelihood of this theta, as we mentioned earlier. So we have to multiply every single data point, okay, from 1 through n, probability of each sample xk given theta, right? So the value of theta that maximizes the likelihood function is considered the most plausible value estimate of theta. So this likelihood function is often transformed using the natural logarithm into log likelihood function, which we call log of theta given x. So this is just simply putting log onto the probability, the original probability function, because instead of multiplying, we can convert it to adding, right? So these are the exponents. So if we simply put the log here, this just becomes a sum from 1 to n log of p xi given theta, right? Okay, so ultimately, maximum likelihood estimation is about finding the maximum value of the likelihood function. Since the logarithm function is monotonic, maximizing the likelihood function, or log likelihood, this one, would yield the same value for theta, because we're just taking the log, right? And we're just now, instead of multiplying them, we're adding them, right? So you can treat this as exponents here. So therefore, for convenience, we can usually maximize the log likelihood function instead of the original likelihood function. So one common method to find the maximum value of the function is by using derivatives. So specifically, for the parameter theta, we can partially differentiate the log likelihood function, this one, and set it equal to 0 to find the value of theta that maximizes the likelihood function. So let's do this. So take a partial derivative respect to theta of log likelihood x given theta given by x. So this is just the same as the partial derivative of theta from sum of n 1 to n log of pxi given theta. Let's set this equal to 0. Okay, so this condition maximizes the theta. So let's estimate mean mu. So instead of now theta, we're estimating mu. Okay, so as you already know, what is our mu hat? This is just an average, right? So given some data points, we add them and then divide it by the number of data points. And estimated population variance is sigma squared hat 1 over 1 through n, and we subtract the mean mu and then square from the original data point for each data point. Now let's confirm this using maximum likelihood estimation. So we want to estimate it to check if these two equations are indeed true. Okay, so assuming each sample is drawn from normal distribution. So what is our probability density function for each sample? The probability density function, so PDF for normally distributed function, normal distribution, is f of xi equal to 1 over sigma square root of 2 pi exponent minus xi minus mu squared over 2 sigma squared. And what is the log likelihood of this? This one is our original likelihood function. So this one is same as x given theta. Now in this case, it will be x given mu. So same as here, let's take a log of this. So what is the likelihood of this function? So x1, x2, all the samples are independently drawn. As I mentioned, we have to multiply all of them, right? So probability of x given theta is equal to, we have to multiply every single data sample. So 1 through n, assume we have n samples, we multiply every function. Since our normal distribution function looks like this, our function is from 1 to n, 1 over sigma square root of 2 pi exponential minus. So let's take a log of this. So the log likelihood of this is, this changes to sum since we do a log. So we apply log here. It would be log 1 over sigma square root of 2 pi minus this value. Now, why? Because if you take a log, this exponential will be gone. Now let's simplify further. I'm going to divide these two values, right? Okay. I'm going to divide this. So sum 1 through n. I'm just going to put this here because this one just got out from the exponent, minus log of sigma, because this was a fraction form, right? Which we take a reciprocal of this, and then also minus log of square root of 2 pi. Now let's partially differentiate this log likelihood function with respect to mu. Partial derivative of likelihood function with respect to mu, right? So this mu is our original theta, right? So instead of theta here, now we're replacing mu. Okay, let's take this one out first. So this is 1 minus 1 over 2 sigma squared sum. I'm just flipping these two. Okay, so this one's here. So this one, and then take a partial derivative because this is where it contains mu. If we calculate the rest of these, what is this? This would be xi squared minus 2xi mu plus mu squared, right? So let's take a partial derivative with respect to mu. Since this doesn't contain mu, this would be a constant. So this is gone. This would become 2 mu, and this would become minus 2xi, right? So this is same as 1 over 2 sigma squared, sum of 1 through n, minus 2xi plus 2 mu. Yes. So, and these two cancels out. And if you flip the minus signs, this becomes 1 over sigma squared, sum from 1 through n, xi minus mu. Okay. And we have to satisfy this condition. And then what is this? I'm going to put mu out of this sum sign. So what do we have to do? We have this one equals to 1 over sigma squared, sum 1 through n, xi minus n mu. Okay, we're just multiplying this n times and take out from this summation notation. So this is sigma squared sum from xi minus mu n mu. This has to equal 0 because this is the condition for maximum likelihood, right? So what is this? This makes our maximum likelihood 0, right? So what is the estimated population mean that maximizes the likelihood? X mu equals 1 over sum from 1 to n xi, right? If you place this here, you would notice that this makes the whole equation 0. Okay, I hope this video helped you understand more about MLE. And if you have any questions, feel free to leave on the comment section, and I'll see you in the next video. Thank you.